So our agenda today, again, we're going to be talking about stiffness analysis and kind of talking about why you need to do stiffness analysis. Obviously, it's one of our other advanced or other analysis types within the connection app. I know we a lot of times focus on stress and strain. A couple months ago, we did the buckling. So we're going to kind of be continuing to kind of mix these in as we go forward to just make sure everyone knows everything that the software can do. So we'll talk about the classification, AISC classifications. This is primarily focused on moment connections. We'll talk about the stiffness analysis within IDEA. Also, the ability to take those stiffness values, those rotational stiffness numbers, and input them back into your global analysis program so you can see how that affects your frame analysis. We'll do a little comparison between the moment diagrams for each of those options. And then finally, just briefly touch on the app IDEA member, which is really meant for analysis of individual members, critical members, and assemblies. So with that, as usual, I'll be handing it off to Andrea to take us forward. Thank you.
All right. Thank you, David. All right, and also a quick note is that the handout is available to download it. I believe it's under the questions pane. There you can download the PDF of this presentation so you can be following along with me. All right. All right. So now let's jump into the first slide. So let's start with some user cases that will help us to understand how and why the stiffness analysis is important. This is, so what I did here is that I gathered some questions or testimonials from users related to the stiffness analysis in IDEA StatiCa. So the first user was asking that, well, he wanted to prove that their moment end plate connections behaves effectively as fully restrained connections based on AISC. So this is one of the main, let's say, use of the stiffness analysis in IDEA StatiCa. But let's continue with the second comment or question from the user. So in this case, the user was mentioning he was using the stiffness analysis for a handful of connections, but there was one in a specific. They wanted to model the behavior of ball group and determine the moment that the semi-rigid connection will generate. So in this case, it is kind of a combination of a stress strain analysis plus stiffness analysis in the application. So he was asking if this can be modeled in IDEA StatiCa. So that was the question, and of course we can do that. Then the third question was more like a modeling question. So he wanted to ensure that all the members were well connected, right? Or the welds were there. So this is more like visually looking at the model, and see that if that you have the welds over there. But as you may have some experience, or well, some of you have experience in this connection design, maybe if you look at one connection, you can see or you can tell if it's a moment connection, right? You have that experience, but until you run the stiffness analysis is when you really know that this is a moment connection or not, right? So again, this was like a modeling question, but our suggestion was also to run a stiffness analysis so he can be sure that he had a moment connection, right? The fourth, let's say, testimonial, this user was sharing with us that he uses the stiffness analysis for HSS moment connections. So he can get a sense of rigidity on the joint. As you know, HSS members are too flexible, right? So it's kind of hard to determine if it's a moment connection or not. So in this case, it's really useful to use IDEA StatiCa and in 2 or 3 minutes running a stiffness analysis and see if you have the rigidity on those connections. He also comments that it will consume a lot of time to input these values back in the structural analysis software, unless they deal with a very complex structure with moment connections, then they'll need to consider this rigorously. So this is a topic we'll talk here, or we'll discuss later on, but this is important, right? To get these values back into the analysis software for these complex situations. Another common question or common user case is when the user wants to know the rotation that is happening at a specific connection on IDEA StatiCa. So in this case, you can use a stiffness analysis and get the rotations. Also, another case is when the universities that we are working on, they run these verification studies and they need the actual moment rotation graphs of the connection. So for instance, for the pre-qualified connections, they were comparing some experiments where they had the experimental moment rotation graphs, but then they wanted to test it in IDEA StatiCa. So this is also a good case because you get the moment rotation characteristics of the connections for whatever connection you are modeling there in IDEA StatiCa. So this is kind of a summary of how the stiffness analysis is used and why, right? The first point is, and the most common, let's say, situation is to ensure the stiffness assumptions, right? Prove that the connection is fully rigid or pin. Then the second is to get rotations, rotation deformation for a given moment, and in some cases get the moment rotation curves for studies. Then another case is the assessment of members already constructed, including the current connection. So when you have already a structure that it's already modeled and you need to assess that member, it's important to assess also the connections in that model, right? Then when we have complex member design with partially restrained connections, for those specific connections, you need to get the characteristic of that connection back into the analysis software, and that is one of the cases we'll see today in this webinar. And finally, another case that I also help with is with bridge connection design. So this was a case where the user was assessing deep girder compression flange bracing. So in this case, as the deep girder is, well, it's kind of tall, it's really flexible. So it is important to consider the real stiffness of these connections from the bracing to the deep girder, right? Right, let's continue. So first of all, let's go to the code, right? Let's review the classification of steel connections from AISC. So in chapter before of the specification, I am using some screenshots from AISC 360 version 2022, all right? And it describes three types of connections. So let me show you this diagram where I like zoom in. So the first type of connection is simple connections, which are the ones that transfer zero or very low moment force into the joint, right? And the rotation of the connected member is allowed. In the moment connection sections, we have two types of connections: fully restrained, which transfer moment forces into the joint, and we must ensure there is no relative rotation, right? And finally, the partially restrained connection, which transfers moments, but relative rotation is permitted, right? So we have a little bit of rotation on those partially restrained connections. So what does that classification mean in the structural analysis? Well, when doing the structural analysis, the engineer must define the connectivity of the members before knowing the detail of the connection. Usually, the engineers define two options, either pin or fix, right? So you can see those in this summary. However, there is no common assumption for a partially restrained connection, as that type of connection is only known once you design the connection of the project, right? Now, let's see how to classify the connection according to AISC. This connection classification definition comes in the commentary section for Chapter B, And this part describes that the connection can be described with a moment rotation curve, right? In the next part of the commentary section, the connection stiffness definitions are presented. And what are the limits value for the rigid and pin classifications? So you will see this graph in the code, well, in the commentary section. And then you can see here the moment versus rotation graph. And this line represents the limit for the rigid connection, and this is the blue one represents the line for the limit for the simple connections. Connections with a stiffness value between those two limits, they are considered partially restrained, right? So if we look further in the commentary section, there is a section for a structural analysis, which I like to highlight 2 points. The first point is mentioning when your connection is classified as PR, so that means partially restrained, the characteristics of the connection must be included in the analysis, right? So you get the real information into the analysis, and then you can determine the member and connection forces, displacements, and the frame stability, right? So it's basically saying that if you have a PR connection, then you need to incorporate the characteristics. So that means moment rotation curve into your analysis, right? And the second point that I want to highlight from this section is that it says that when the connections do not fall within the database's ranges, it may be possible to use finite element studies, like in this case, we are going to do it with IDEA StatiCa, right? Now, let's review the process to run stiffness analysis in IDEA StatiCa. This is a high-level, step-by-step process, but if you follow the link in that PDF that I put you, and then you have this link here, if you click over there, you will get a detailed tutorial of how to do this stiffness analysis in IDEA StatiCa. But again, let's review the steps. The first step that we recommend is to perform an stress-strain analysis first. That means you will run the regular analysis that we have, right? So you can ensure that your model is correctly modeled, like you don't have any modeling issues. So later you cannot have errors in your results for the stiffness analysis, right? So that is my first recommendation. Run an stress-strain analysis and make sure your connection is okay, right? Then you can copy that file, copy that connection in the application, and then change the analysis type to a stiffness analysis. So let's review that step-by-step process. So in this second step, as I said, you do a copy of that connection, and then you can come here into the title of this connection that it's below the cube, where you can rotate the view. So you click over there, and here you will have the parameter, well, the descriptions and the name of this item in the file. And then from here, you can change the analysis type to stiffness analysis. Also, you can see that we have all the other types of analysis available over there, right? So that's how you change the analysis type. Now, once you change that, it's important to select the analyzed member. Why? Because when we run the stiffness analysis, we only assess one member, right? It's when you have like two members here, like the column and the beam. Of course, you want to assess the stiffness from this member to the column. So you can right-click over here and you set that as analyzed member, right? Because this is a long, analysis. We do behind the scenes, we do many analysis types. It will be just too long to, for instance, if you have this type of joint, to do the analysis for all the members at the same time, right? So that's why we need to set up which one is your analyzed member. And then if that is the case where you have many members in one joint, all the other members are fixed, right? So they are like rigid. So we're just focusing on the stiffness from this member to the column, right? So third step, select the analyze member. Fourth step, once you select the member, two new fields will appear in this characteristics of the members. So if I go back here, when you're looking at the member properties, at the bottom, you will see that you will have these new two fields. They are called theoretical length for MY or for MC. So let me go back. There you go. So these fields are related to the theoretical length that is taken for the stiffness analysis, right? These lengths have a behavior similar to the buckling lengths, right? These are the geometrical distances between the supports, which will be related to the bending of the member, right? So we have an input for MY and MC, which are related to the bending in Y and C local axis of the member, of course, right? Depending which rotational stiffness you are calculating, the input you use, right? An example with a different theoretical length for each direction could be, for instance, a roof beam, right? Because it can have maybe stiffeners to restrain rotation in only one side, right? So here you can see the comparison between the MY theoretical length. So in this case, it's the whole length, right? And for MC, like in this case, maybe you have a stiffener every like 2 feet or whatever distance you have there. So that is restraining the bending in that direction, right? In the C direction. So this maybe can have a different theoretical length for MC, and this will be a different theoretical length for MY, even though it's the same beam, all right? And another important point to mention here is that this only affects the classification limits, not the stiffness itself of the member and the connection. All right? In the fifth step, as mentioned, only one member is analyzed to avoid long calculation times. Also, IDEA StatiCa doesn't evaluate stiffness for all the degrees of freedom, only the ones that you specify by inputting the forces of the degrees of freedom that you want and stiffness calculation, right? So when you're in the model and you specify, when you input a force on MY, you're telling the software that you want to calculate the rotational stiffness around local Y axis. And then if you input a force on MC in the loads table, then you specify the software that you want to calculate the rotational stiffness around local C axis. And the same for the actual stiffness. So IDEA StatiCa can calculate rotational and actual stiffness. And then if you want to calculate the actual stiffness, just put an actual force in the member. All right, that's the way we activate these calculations. All right. Now let's continue to the next slide. So once you set up the forces and then you hit calculate, so let me explain what happens or behind the scenes. So to get the moment rotation curve of a connection, IDEA does two types of analysis internally. The first is to assess the rotation, right? And the second is to learn the connection ultimate resistance. With those analyses, IDEA constructs the moment rotation curve. Let's review these two types of analysis. So when calculating the moment rotation curve, so that means assessing the rotation, right? So the software applies load steps, so that means bending moments, and evaluates the rotation, right? So as you can see here, we are getting the rotation caused by the connection. So to get this rotation generated only by the connection elements, two analyses are done. you can see the overall and the members. So one analysis is done considering the overall model. Okay, so you can see here the overall model, including members and connection. And the second analysis, it's considering only wireframe elements, and they are connected rigidly, with a rigid link. And in that way, we can subtract from the overall rotation behavior, we subtract the members' rotation, and finally, we get the rotation created by the connection, right? So this is the value we are worried about, okay? Then we also need to get the ultimate rotation capacity. So the software iterates and it stops the analysis till either the bolts, anchors, or weld resistance is reached, and the plastic strain limit in this case is 15%. Remember, this is only to get the ultimate rotation capacity, all right? So these are like the limit values for that rotation capacity. The second analysis behind the scene is to get the connection ultimate resistance, which will be used to construct the stiffness curve, as we mentioned, right? In this case, this is identical to the joint design resistance analysis. In this case, the resistance of the connection is reached once the plastic strain in plates hits either 5% of the plastic strain, or the bolts, anchors, or welds resistance is reached, okay? So this is also important so we can assess the whole thing in the results. So now let's review the results. Once the analysis finish, you will go to the check tab, and then you will see this tab over here. So when you click over there, you will get this table here and this graph, right? So let's discuss these results here. And by the way, in that PDF, I added like the extended version of this presentation, and you have the definitions of every result in this table in that PDF, all right? But anyway, I'll explain it during this webinar. So first of all, you will see what is the item that was analyzed. So that is the member. So in this case was member B. Then the component that was analyzed, in this case, it was MY, right? So we're analyzing the rotational stiffness of MY around Y-axis, okay? And then the load effect name. So in this case, it happens that I put the same name as MY. So, but in this case, you can have the load combination name that you prefer, right? The first value that we get is the MED. So if you see here, I have the definitions of all the moments because they have a line over here in this graph. And it's, in this case, the MED is the design moment. So what is that design moment? Well, that is the moment that you input on MY in this case. So this is my input moment, okay, to get this analysis to run. Then the next cell is MJRD. So that is the maximum bending resistance of this connection, right? As we reviewed before, we run the ultimate resistance of the connection, and we need this value. So we need the maximum moment capacity of the joint, right? Next, you can see that we have initial stiffness and second stiffness. Okay, let's explain what is this initial stiffness. The definition of the initial stiffness is the value where the behavior of the connection is still linear, right? If you look at this graph, that it's the green line represents the stiffness, right? And with this line, somehow you can see the behavior of this connection, right? At the first part, this is behaving in a linear manner, okay? So to calculate the initial stiffness, we're using 2/3 of the bending resistance. So we multiply 2/3 of this value, in this case 600, and then we draw here a line, right? So in this case it was 400, and in the point where we have the stiffness curve and it touches that 2/3 of mGRD, that is the value that we are showing you. So this is the stiffness while this connection was linear, okay? And you will say, well, from where this is coming? So this is coming from Eurocode, okay? I have common questions usually like why we're not doing as AISC mentions. We'll review that in the next slides, but there is no specific way to calculate this initial stiffness. However, the important stiffness that we need is this second stiffness, right? So let me explain you what is that second stiffness. This is the value of the stiffness calculated as the intersection of the input design moment. So this stiffness is the one related to the input moment, right? So that is the one that we'll use later on when we are using the stiffness results, all right? And if you see, you can see the design moment line here in this graph, and where it touches the rotational capacity, or sorry, rotational or the rotation degree, that is the value that we are putting over here in the second stiffness. So basically, you can divide the input moment by the rotation for that moment, and you will get this second stiffness, all right? Then we have two phi values. One is phi, and then the other is phi c. So the phi value is the rotational deformation at the given moment, right? Remember, this rotation is related to the moment we input. Then we have phi c. So that is the rotational capacity of the connection. So I draw this line to represent where is that rotational capacity. So it is almost at the end. Remember that we, to calculate this rotational capacity, we use a higher limit, that it's 15% of plastic strength, right? So that's why we need these two types of analysis behind the scenes, because we get the moment capacity and the rotational capacity, okay? Now, the L is the theoretical length that we explained before, and then we have these limit values, right? So this is the fully restrained limit value. So you can see the yellow line I am marking here, the fully restrained limit value, and then the pin limit value. So this is also that value, and these two are calculated from AISC, from the formulas of AISC. Finally, we get the classification of this connection. So if it's between these two limits, then we have a semi-rigid connection, okay? Now, what you can do with this graph, if you right-click over this screen, you can send this to an Excel file or a file with extension CSV, right? And then you can open that in Excel, or you can send the picture. Well, you can save it as a picture, this graph, and then obviously you can take these values to wherever you need it. So I have this slide to show you how you can get, you know, the graph in Excel. I did this video. I'll post it also in the main website of the webinar, right? But with these values that you get in Excel, you can create your own graph. So actually I can play this. So you'll get it as a text here. So you can convert this text into columns, right? So I am using the Excel functionality, and that is delimited by semicolons. So you can select that, and that will create automatically the two columns there. And then with those two columns, then you can create your graph in Excel. Of course, this has the same unit that you select in IDEA StatiCa, and then you can change that unit. There is no problem with that. Then you start modifying your diagram with the Excel capabilities, and then you'll have this nice graph. But another important thing is that from here, let me just go back to this part of the video, is that you get the X and Y values. So that means this is the moment versus the rotation values, right? That probably later you can use, okay? So let's continue. Let's continue with, let's go back now to the code to show you what is the AISC definition of the initial stiffness and second stiffness. So it's, I am highlighting this important part where it says, like many connection types do not exhibit reliable initial stiffness. So in this case, the stiffness that we worry about is the second stiffness. But you can see here that it says that the second stiffness at service loads is taken as an index property of the connection stiffness, all right? So that means that the second stiffness, it's calculated with the service load combinations, okay? So to calculate this second stiffness, the input value should be the one from, well, the moment result from the load combinations for serviceability, right? So for instance, if you get a connection and in the analysis you have the strength load combinations and then the service load combination, the moment that you will use will be the end reaction from the service load combinations. So in that case, when you use that moment, you are following the AISC requirements, right? So that's why it's important to input the correct value in the forces when you're analyzing the stiffness, okay? Now, what to do with these results? First of all, we can confirm the assumption if it's a pin or rigid connection, right? As we saw before in the first couple of slides, the users were asking how to confirm these assumptions, right? To really see if your connection is fully rigid. So this is only to confirm those assumptions. However, if you have a partially restrained connection, and if that connection is really needed like that, right? If you cannot change the design of that connection, right? Then you need to input those stiffness values in the global analysis software to model the actual behavior of the connection and recalculate the member design. This is not from my point of view, this is from the AISC commentary section, right? Then after the stiffness analysis is done, you can set the rotational stiffness in joints of the global analysis model. So you can import those values as a single value, and here we have some recommendations, or as a nonlinear function. So let's see what are those two options. So to input those moment rotation characteristics in the global analysis software, there are two options, as I said. And the first one that I am highlighting here is a moment rotation plot or a nonlinear spring. Some applications, some softwares like SAP 2000, ETAPS, and MIDAS, you can input the actual curve. So in this case, this is an example from MIDAS, and I am putting here a link how that is done. But you can actually put that curve there, rotation versus moment or vice versa, right? And that spring will be modeled in the main global analysis software. Then the second option is to use the single value. So that means that is a linear spring, right? And the majority of the software have that capability. Like in this case, you can see a screenshot here of STAAD.Pro. In this case, you input that as a member specification, and that is a release either at the start or at the end of that member, right? And then you activate the stiffness constant that you want to add. Make sure you have the same units, right? In this case, I change it to keep 5 degrees to match my units in IDEA StatiCa. If we look at the commentary section, B3 again, in the structural analysis and design section, we discussed that before, but I am showing just this part. It says that for serviceability, an analysis using linear springs with a stiffness given by key S is sufficient, all right? If the resistance demanded of the connection is well below the strength. So this is making the process a little bit easy, right? Instead of putting, you know, the nonlinear spring in the model. But again, as it says here in this portion, the degree of sophistication of the analysis depends on the problem at hand, right? So again, a lot of engineering judgment is needed. However, IDEA StatiCa is giving you these tools to doing it in the correct way. Okay. All right. Let's continue here. So, like an exercise, I did this simple frame example using STAAD.Pro and then IDEA StatiCa. And I recommended you also do this if you are curious about, you know, the behavior of and how the stiffness change everything or change the moment diagram in your main beam. But start with a simple example as I did here, right? So I started by modeling a simple frame in STAAD.Pro, right? I use rigid assumptions. So that means the beam to the column connection was rigid link. And then I added loads. This was a linear load, simple linear load in the beams, and then I added a lateral load in this corner here, right? And then I created the strength and service load combinations. And finally, I ran the analysis. So once I got the results of all the members, then I exported it to Checkbot. Remember that we can export the whole structure to Checkbot, and then let me zoom in here. And then in Checkbot, this is just a screenshot, you can see that I have all the members here, and I model all the connections, like the beam to column and the base plates. So you can see the connections here listed, or all were okay. So I designed those connections, and then I run also stiffness analysis, right? Because that was the main objective. So once I, you know, designed the connection, I did a copy in that same item, and then I run the stiffness analysis. If you look here in this result that I got, you can see that the analysis can be run for different load combinations. Although it's not recommended, but if you want to just compare two load combinations, it's okay. That won't change. I mean, the input value won't change the type of connection you have, because that is independent, right? One thing is the stiffness of the connection, and the other part is what force you are inputting there. But anyway, I use the service load combination here. You can see this is the line, and this is the stiffness I use to go back to STAAD.Pro and put it in the linear spring. Okay, so I did this for the important connections, because I wanted to analyze like this member and this other member, so I had to run the stiffness analysis for this one, and this other, right, for the 3 connections. So once I got those values, then I go back to STAAD.Pro, right? Let me zoom in here. And you can see that I added this specification for beam elements. So you click over the beam, and then you can see this release. So you can add it at the start or the end of that member, and then you add that value over there. So in this case, it's only a linear spring, only one constant, okay? And you can see that this is highlighted over here. And then I rerun the analysis in STAAD.Pro with these values, okay? So let's take a look at the results. So first, let me explain what you're looking here, what you're seeing here. So these are Checkbot moment diagram views, okay? remember that in Checkbot you can see the moment diagram on the members. All right, we have this this view there, and in the first iteration, well, I took this screenshot here, right? And also you can update the model with the changes, with the load changes, right? So that's why I have the two models in just one checkbot, let's say, right? And then I took the screenshot for the rigid assumption results and with linear stiffness assumption, or with the spring constant, right? So what we're, and of course the results are from STAAD.Pro, right? So what we're looking here, so if you look at the moments in this joint, you can see from the rigid assumption to the linear stiffness, or to the second iteration, they were actually reduced, right, on the joint. However, the one that we are worried about is the one on the member, the moment at the central part of the member, right? So from the rigid assumption to the example with the linear stiffness, okay, we got an increase on the member. That's why you need to get back to the software and input those stiffness values in the element, well, at the end of the members, and then that's why the code is asking you to redesign this. Maybe this is not a huge difference, right? But when you have a more complex design, or when you have a different type of section that it's not a Y-flange element, this can be critical, right? So again, we are looking at the service loads results only, okay? So yeah, so that's why this is really important when you have these partially restrained connections. Now let's look at the next comparison that I did. So another important thing to look at is the total deflection, or the drifts in this case, right? So I just wanted to make it simple here. So I am showing you the rigid assumption and with the linear spring and only the service loads, all right? And you can see how the total deflection was increased from the first case to the second case, right? Again, you may say, like, this is not that a big change, right? But there is a change. And remember, when you have a more complex design or a more critical element, this is really important, right? Now let's look at the connection results here. What was changed with the rigid assumption versus the results with the linear spring? As we see at the start, well, in this comparison, you will see, you saw that the moment was actually reduced, right? So with the rigid assumption, we have a maximum plastic strain of 0.4, right? If we look at the linear spring assumption, well, with the stiffness value, you can see that that plastic strain was reduced, right? So I mean, the maximum plastic strain was reduced. For the connection, it's probably not that big change, right? It's actually helping it. However, it's important to reassess only for the member design, right? Okay, now let's jump to the final part of this presentation. One important thing to remind you is that if you have IDEA StatiCa, if you have the steel model, probably you have access to IDEA member, right? And let me describe you what is IDEA member. IDEA member does FEA analysis and design of member using shell elements. And you can include the actual connection model in that in those elements. So this model that I am going to show you was opened from Checkbot. And then the forces are also imported from STAAD.Pro. As I had the connections in the model, because I modeled them before, they came also in the member model. So actually, I didn't have to do many modeling. I just selected the members, as you can see here. I created a member file from here, from Checkbot, selected those members, and then I open it from here, from Checkbot. And frame was exported from Checkbot in member app, forces also exported from STAAD.Pro, well, they were here already, and also the connections from IDEA StatiCa connection, right? So once I open, this is an actual screenshot of member application. Once I open that model, you can see that I am considering 3 elements or 3 members here, right? And I have the loads coming also from STAAD.Pro, so I didn't have to remodel those loads there. And then I also have the connections. If I zoom in here, you can see them, all the connections there, right? So in this case, there is no need to use the stiffness analysis to input the stiffness constant in IDEA member. Why? Well, the connections are modeled there, as I show you, and analyze it together with the frame. So the connection stiffness is included in the moment diagram calculation. So you can see here that we also can show you the moment diagram in this structure, all right? So this is the moment diagram using the service load combination in IDEA member. So this is the result from IDEA member. Then, now let's compare this to STAAD.Pro analysis, right? It is important to mention that to compare these two, I had to calculate the stiffness for all the joints here. As you can see, this is small. Let me, yeah. See, you can see this small circles that are representing the release with the stiffness value, right? So I had to input those values here, here, and here because they were the same, let's say, I mean, I wanted to focus on these 2 members, right? Just like in member. And I had to put those values in the STAAD.Pro, all right? So in that case, you can see that the moments are almost equal, right? So if we look at the moment in this one, it's 106. Maybe you cannot see it really well. 106 for this member. And this is 107. And then if we look at the central portion of M7, it's 71.74 and 72. All right. So what is the takeaway from here? Well, by using IDEA member, I didn't have to do, you know, this iteration between IDEA StatiCa connection and IDEA member. So I just come here directly and model those members, well, importing those members from Checkbot and run the analysis and get the most accurate moment diagram, right? And values. So, all right, let's jump into this summary of this webinar. So takeaways, you can confirm the assumptions by running stiffness analysis, confirm your connections or joint assumptions, right? Second takeaway or highlight, make sure you use the service combination to calculate the stiffness when using AISC, right? If for some reason a partially restraint is needed, you can use IDEA StatiCa to input the stiffness constant in the analysis software, okay? Depending on the problem, select if you use a nonlinear spring or linear spring in your analysis software. Many resources about the topic are available. IDEA StatiCa eases the calculation. And remember, use your engineering judgment, right? Finally, IDEA member is a tool that can help you to analyze and design complex members as the connection stiffness is included. So no iterations are needed. You can just go right away and get the exact values. All right. Well, that's the end of the presentation. I just have, well, we have the